This tutorial is going to explain how we can use elastic scattering spectroscopy to measure the size of something in a cell. And what I mean by that is that we're going to measure intensities as a function of wavelength or intensities as a function of scattering angle. And in either case, the goal is to get a size estimate, say of the nucleus or of the other organelles inside of a cell. Before we get into actually shining light onto a cell, let's establish just how sensitive light can be to changes in size. So we'll set up a simple situation that's not specific to cells. We're going to think of a little slab geometry where there's some little region, 3 refractive index regions, with this region of interest is N1. This is sort of playing the role of the thing we want to know the thickness of. And then on the left and right of it, we have some other refractive index N2. And if we sent in some beam of light at some laser wavelength, we could imagine light reflecting off of this N2, N1 interface and sending light back. We're going to call that beam A. And we can also think about light that travels into region N1 like that, reflects off of this surface, and then comes back and transmits through this surface. And we could call that beam B. And then A and B can interfere with each other. And the point of elastic scattering spectroscopy comes down to the fact that very small changes in this thickness D of this region can be measured by the interference between 2 beams A and B. And the changes that can be measured are small fractions of the wavelength of light. So if we interfere A and B, the total field that we're measuring, EA plus EB, what's that going to be? Well, there's some initial electric field that was sent in there. Maybe we call that E0. And then beam A reflected off with some reflection coefficient. I'm going to call that R21 because it went from medium 2 and reflected off of medium 1. That's the Fresnel reflection coefficient, I mean. And then the series of events that leads to the B beam coming out is a transmission from 2 to 1, a reflection of interface 1 against 2, and then the transmission on the way back is transmission 1, 2. And then there's also a phase that's accumulated over this travel distance. And I'm just going to, for the moment, going to write that as e to the I phi round trip. Now, what is the phase accumulated on that round trip? Phi RT for round trip. It equals the wave number in vacuum, 2 pi over lambda naught. So lambda naught will be the wavelength of this light if it were in vacuum, times the refractive index of this middle region where it's doing this extra traveling and picking up this extra phase, times the total distance that it travels in this region, which is the round trip there and back, 2d. Now, we will notice that Fresnel reflection coefficients for simpler problems like this, the reflection coefficient R12, that just equals the negative of R21. I'm not going to prove that for you. But what that means is that we can write this overall electric field here. We can factor out the E0 R2, and then we've got 1 minus some constant here. I'll just call it C1. I don't care what it is for this derivation. And then an e to the I phi. So you can already see that this 1 minus something e to the I phi, it's probably going to give us a sine term. And let me just quickly make that happen for us. I can even rewrite this expression here as some E1, that's just the constant amount without a phase term, plus an E2, which is 1 minus e to the I phi round trip. And I can rewrite that even further. I'll just skip a few steps for converting 1 minus e to the I phi RT into a sine term. I'll write this expression now as EA as the constant and some amount of EB times the sine of phi round trip over 2. That's what this turns into. And I can rewrite that as EA plus EB, and if I just substitute in for what phi round trip is, I get it's 2 pi times this ratio of d over the wavelength divided by n1. And the reason I'm going to all these lengths is to show that we now have an electric field and eventually an intensity, if we measure it, that has a sign dependence in it that can go from a minimum value if this red term here is an integer, if d is equal to some integer multiple of lambda over n1, and if I increase it to a half integer, then the sign becomes an extremum. So what that means is that I can see a big change in this second term over here. It goes from an extreme value to a null value for delta d of 1/2 this value of lambda naught over n1. So again, if d over n1 is an integer and I add this amount here to d, I will take sign from being a null to being an extremum. And so if I look at what this extra amount of diameter change is, that takes us from a max to a null, if I had, say, 500 nanometer light, this would be 500 nanometers divided by 2 times the refractive index, which might be something like 1.4 for tissue. So we're getting up to a range here where 500 divided by 2 is already 250 nanometers, and then we're dividing by a little bit more, so we're in the neighborhood of 200 nanometers. And that's a change in the intensity that if I go all the way from a null to an extremum, if I have a system that can measure more subtly than that, I can probably take this down to maybe the 10 nanometer regime. It will all depend upon how sensitive my system is to measuring small intensity changes. Point being that a visible wavelength of light can sense much smaller changes in the size of one object relative to another, or the swelling of an object if it changes in time, much less than the wavelength of light itself. You can get down to 200 nanometers, 10 nanometers, it depends on the quality of your system, but nothing fundamentally limits you from sensing a 10 nanometer change. All right, so we'll wall that off. Let's just now go through the actual case of if you've got a target that's a sphere. And the reason we care about spheres is, for instance, we might be interested in the size of a nucleus. When there's a cancer, the nucleus tends to swell. So that's something that people actually go out and measure. And we're going to think about, I'm drawing some parallel wavefronts here so we can talk about a light beam shining in this direction. And there are some additional factors that come up when we're in 3D. So let's label this the 3D discussion of this tutorial. The analogy to what's going on up here is that if you send a beam in like this, you could have if we just think about rays approximately, we could have a reflection off the front surface A, and we could have light that goes through the nucleus, bounces off the back surface, and comes out here, and that would be our beam B. But there's an additional factor to think about here, that because this is an object that's confined in all dimensions rather than this slab here, which was infinite in 2 of its 3 dimensions, we could send in light at some different part of the nucleus of this sphere, not dead center on here, and then the reflection might bounce off that way, and not even trying to take into account refractive effects, just sort of looking at geometry here, you can see that the reflection that would give us the interference with that, we're now at some different angle here, some theta, that's not a perfect backscatter direction, and that extra path length that's been accrued in the cell not passing through its thickest point, as I was trying to indicate here, we're going to have a dependence not only upon the wavelength of the light, which clearly affected its measurement in this case, and for the same reason in this case, but now we have an angle effect because it's a confined particle, and depending upon what part of it we pass through, we get a different path length difference between the black and the red rays here. So we have angle dependence and we have wavelength dependence. So this one is emphasizing angle dependent changes in the strength of signal that you'll measure, and this one up here was emphasizing lambda dependent. So we have these two things. That's why in the title up here, we talked about measuring intensities versus wavelength, or intensities versus angle. Okay, now this paradigm up here where we send a plane wave in to scatter off of some target sphere, that's a well-defined physics problem, and it has a name because someone named Gustav Mie wrote down the original solutions for it in the early 1900s. So we talk about things like Mie theory. It's not the only theory, but it's the one I'll focus on here. When we have a scatterer, a sphere, being irradiated by a plane wave, theory allows us to calculate the scattering that we will measure as a function of a given angle of scatter and a given wavelength of illumination. We can now map those things out. And in this particular class, I will come right out and say we don't calculate this ourselves. There are a lot of calculation engines out there, and our book has information about it. The point is that this is a solvable problem. The rest of this tutorial is about figuring out what do you do once you've got access to this theory. How can you make measurements that you can compare to theory and that extract the size of something. And there are two different things that we're going to encounter in this game. The first thing we have to think about is if we have a thin sample. So with thin samples, the measurement geometry can be relatively straightforward. You would have a sample like a little cell like this that you might want to study, and you might place it in the path of a plane wave, as I said. So here comes the plane wave. And one thing we might choose to do is irradiate it at a single wavelength. And then light would scatter from it in various directions. Here I'm drawing it in the forward direction, but you could also measure backward scattered light. Now there's also going to be, for this plane wave coming in, there's going to be unscattered light. I'll call this unscat. And we need to dump that. So that's a measurement you're not going to want to make because you're not measuring just scattered light. You're mostly measuring unscattered light. The cells are pretty weak scatterers, so the amount of forward scattered light is pretty small compared to the unscattered light. So in this paradigm, you send in a single wavelength and you measure many angles. And there are various experimental techniques for measuring the scattering happening at different angles. You can swing a detector into different positions here. You can use a lens and focus this light in a certain way onto an array detector, and different regions of the detector will be collecting different angles simultaneously. The net result of doing this, however, is that you get a plot where if the x-axis is scattering polar angle, there's going to be some theta minimum that your measurement starts at, because you can't really measure anything at 0 degrees. And then you get some signal pattern like this. It won't always have ripples like that, but I'm just drawing that for an example. So this is what your data look like. This is intensity as a function of theta. Another possibility, though, for your geometry is that you could have the same target sample. You could have the same geometry of a plane wave coming in, but you could have a many wavelength source, like a light bulb. And in this case, you're still going to have an unscattered direction that you don't want to measure. And in this case, the scattered light, you can just measure it going off in some particular direction like here, and you only have to measure a single angle. So in this case, your plotted data, now you're measuring versus angle. Now there's no equivalent to a theta minimum. There's just a lambda min that you have here, but it doesn't have any constraint on what it can be. And there's going to be a lambda maximum here. These are just set by your light source, whereas theta minimum is set by how close you can get to the unscattered beam, how well collimated your input light is. And this is also, as a function of lambda now, going to be some data that may have some oscillation ripples in it. So these are both strategies that work equally well for forward scattered or backward scattered light. In either case, you just have to avoid, in the forward direction, you have to avoid the unscattered light. In the backscattering direction, you can take the light directly at 180 degrees, of course, and you can measure versus angle or versus wavelength. As long as you confine yourselves to having a single thing of one and many of the other, it doesn't matter which one is single and which one is many. You can do a nice fit to this, and the features don't wash out, and you can measure the size of something. The really important thing for biomedical optics is that we're often not presented with a thin sample. This stuff is good if you have a cell or a cell monolayer on a microscope slide. But what if you want to measure a tissue? What if you have an intact bulk tissue? So you now have thick samples. So the geometry of a thick sample that matters is a situation where you might have a layer with some scatterers in it that's near the surface. These might be nuclei, I'll shade them in a bit, that are inside of various cells. And this might be some lining tissue. And then underneath that, there might be some other tissue that we're not as interested in. So we might be wanting to study, say, cancerous developments in some lining area of the skin or the esophagus or various other places in the body. So the geometry of this measurement would be to do something in a backscattering mode. You'll see why in a minute. So if you send light in at near normal incidence, I'm offsetting this from normal incidence just for clarity, there would be our in photon path. And then on the way back at almost 180 degrees bounce, as drawn, truly at 180 degrees. What I'm drawing here in red is what I drew in black up here, I guess. This is light that goes in, scatters off of one of these cells, and immediately comes back out again, a singly scattered photon. And then in blue, what I'm going to suggest is that light might come in, hit this cell, scatter off again, off of something, go over here, scatter off of something. Maybe it comes back to really close to where it came in, and then that light might happen to scatter out in the exact same direction. So again, we've got two ensembles of light to think about. The single scatter and this multiple scatter. And just to label this top thing here is what we might call some epithelial tissue, as I said. And then these down here are just some lower layer. It will depend upon where you are in the body. Okay, so we're going to play a trick here that's going to enable us to analyze single scattering from this cell layer or small thickness region as if it was like this case where there was no layer beneath it. Seems hard to do that. However, we're going to exploit a particular thing. We're going to exploit polarization of light. So we haven't talked about this up to date in our class, but a light beam can be sent through a polarizer and be polarized so that the electric field oscillations are all in a particular direction. So if we have a single scattering situation, that's the red in, red out scenario there. What's happening there is we can have light coming in, and I'm going to draw this little arrow here to indicate the polarization of the incoming light. So we got light coming in. Its electric field is oscillating in the plane of the board here. And what it excites in the scatterer that it scatters from, if this were coming in truly from vertical as you see it, we would be exciting some dipole moment here. I'll draw that as a lowercase p naught. And so charge is shaking back and forth in this scatterer. And if I look at the radiation that's sent essentially straight back up again, offset just for clarity, that's the out beam. And the physics of it is that the outgoing beam is also going to be polarized in the plane of the page. So basically the same polarization as what went in, if you think of it as a true 180 degree backscatter. So it maintains the polarization. Now let's consider what happens with multiple scatter. So if we just redraw this path of what's happening over here, we have light coming in, then it scatters a bunch of times. Just redrawing what I had over here. And then it comes out of the tissue. Each time that this stuff scatters, there's a different location at which it scatters. And when the photon travels off at some other direction, it excites a dipole in different directions at all of these locations. Only in the first case, when it's coming straight in from above, is that dipole moment shaking exactly horizontally. In general, it's oriented in some other three-dimensional direction that isn't exactly this horizontal here. And we can talk about this more in class, but the point is that multiple scattering events like this lead to an output polarization which is equal parts matching the polarization that went in and orthogonal in and out of the board to the polarization that went in. If we average over all the different paths that are being created in this turbid tissue and then eventually come out and reach to our detector, it's equal amounts. What are the consequences here? What measurements do we want to make? Well, let's name these things first of all. If we say that all of this light that came out parallel to the incident light, we're going to name that parallel light. And that's a measurement that we can make. We can send in light through a polarizer and take light back and pass it through the same polarizer. With a little more effort, we can also think about if we have equal amounts of parallel light, meaning this orientation here, and perpendicular, that's this orthogonal component here. We could also measure the perpendicular component of the light that comes back. We just have to pass it through the proper polarizer. So the measurements that we make to do this polarization trick are we measure the total intensity that comes back to our detector parallel to the incident polarization, and that's going to be a combination of two components. It's going to be the parallel component of the diffuse light, I diff. Here's the diffuse light, or multiple scatter, and some component of that is going to be parallel. And then there's also going to be an I parallel for single scatter. And similarly, we can write the same thing for the perpendicular component. It's going to have a perpendicular component due to diffusely scattered light, and it's going to have a perpendicular component due to singly scattered light. Then we start making arguments. We say the single scattering is all coming out parallel. So this term I perpendicular single, that goes to 0. And this argument here, on the multiple scatter, the diffuse scattering, that the light coming out has equal amounts of electric field on average contributing to parallel and perpendicular measurements, means that these two terms are equal. And the takeaway from that is that if I measure I parallel and I subtract off I perpendicular, these two terms will cancel. This term is 0, and that just equals I perpendicular single. And that's pretty remarkable, because that means that we have an experimental measurement of just the singly scattered light, the red light indicated here, by making two measurements and canceling out the randomization stuff that happens in the bulk tissue. We come back to having a measurement just of singly scattered light, and that's a powerful way to size nuclei in an epithelial layer on top of a thick tissue region that you don't physically get rid of, but whose scattering properties, as they affect light scattering versus wavelength, you can actually ignore.